Hello everyone, welcome to Learning Express YouTube channel. So friends, today in this video we will continue CTQ10 with the noise analysis of these two circuits. Okay, so in previous two videos of this particular CTQ, we have discussed the gain calculation, swing analysis with practical and ideal current sources. Now we'll see the noise performance and which circuit is better is our target to analyze. Okay, so we'll see how to analyze two circuits on their noise performance base. So the important thing is here the noise analysis. Okay, so in this circuit what our target is the noise analysis of the circuits. So first I'll take the first circuit, and the important thing that I want to make here, I'll use the practical current sources. Practical current sources that we have used in the previous part of the CTQ while we are calculating or discussing the swing calculation. So practical current sources for noise point of view. So just I will make one point here. When we will analyze the noise, it is a your let's say noisy transistor. Then we can model a noise current source in parallel to it, which is nothing but IN of this transistor's noise, and this is now noiseless. Okay, so previously it was noisy, now it is noiseless. One more thing that I can make here is I can model the noise for this transistor in the series of its gate as a series this transistor's noise voltage. Okay, so what is this noise current? In general we make it as 4 kt gamma gm of this transistor. This is the average value of noise current which is modeled for this transistor, and this voltage, which is nothing but when we want to come from output current to the input voltage, then what is the relation that we always follow? This INM, when we divide this average noise current with the GM of this transistor, we comes at the average value of noise current and the voltage input. Okay, so what it will be? So from here we can see VNM as INM, and what is the GM for this transistor, which is nothing but GM. So overall what we can say, it is nothing but 4 kt gamma by GM. So this is the average value. Okay, and the mean square values, usually we write the quantity in terms of mean square value, which is also called the noise power. Then it is 4 kt gamma gm, and what is the mean square noise current, sorry, noise voltage at the input, which is nothing but divided by, then it will be divided by gm square. Okay, then it will be 4 kt gamma by gm. So usually we represent this noise quantity in terms of mean square value, which is called the noise power. Okay, so the mean square value also called the noise power. So we represent noise in the mean square value, which is also called power. Okay, yes, it is a random quantity where we can represent it as a mean square value. Okay, so this is the point that I want to make for the transistors. For the resistors, we know for the resistors noise, if it is a noisy resistor, if it is a noisy resistor, then if I want to model it as a noisy, sorry, if I want to represent as a, it is the noise voltage, then what will the representation? It is nothing but, okay, yeah, it is nothing but 4 ktr. Yes, so the mean square value for the resistor's noise is 4 ktr, and this is the one way of representation of modeling of the noise for the noisy resistor. Now it is noiseless because we have extracted out the noise source. Now it is noiseless. And other way of its modeling is when we want to model the noise, we can model it as a parallel current source also. So now this is a noiseless resistor, and this is IN. Our average is nothing but 4 kTr by R, because voltage divided by resistor is your current. So in the mean square value, how we can write as 4 kTr by R square. So it can be written as 4 kt by R. Okay, where K is a voltage main constant, R is the resistor. So this is the noiseless now. Okay, so these are the one point that I have to make. The gamma here is a empirical value. Usually we take the gamma as a 2 by 3. In many cases we have seen in the many books it is written as a 2 by 3. I will not tell exactly what is there, but it is 2 by 3 you can consider. Okay, in some cases it's a 1 also. So this is just a basic fundamental of the noise. Now we will switch and analyze both the circuits. So first I will take the first circuit with the practical current sources. Okay, yeah. So actually I should not mention the input, because in the noise analysis we make the input as a short. Anyway, I am just considering first the diagram, then we will see how to analyze it properly with this noise modeling of this transistor. This is N bias. As of now I am mentioning, but as soon as I start the noise discussion I will remove it. Okay, so just your A BD or BD. Okay, this is your P bias. PB is nothing but P bias. This is my out 1, this is my out. Okay, I want to see the noise contribution of tail source first. There is a uh, something hidden in the tail current. Okay, so the rest everything is same, but here I want to see first. This is my M naught, the tail current source noise. Tail current source noise contribution. So we will start with it. Okay, yeah. So what can we see? No, now I'll not go to the top. I will start here. This is to be shorted, and this is my V noise 1 at out. Okay, I will write like this. This is the average value. And here is my resistor, and this transistor biased like this. Okay, so other transistor here, noise 2 at output like this. And one more thing that I want to make you clear here, if I split this noise current, which I will model as, this is a noise current for this transistor, which I will call IN0 average value. Okay, so what we can see from here, that at upper side both the circuits are looking same. So what I can see, the up impedance for both the sides is same. Let it call R up 1, this is called R up 2. Okay, so when we look upside we'll see that both the circuits are identical, so R up 1 equal to R up 2. So what I can see, this current source, ideally speaking, if there are two similar impedances or same impedance at the top, and this is your noise current, just I'm just avoiding or removing this M naught transistor, which is a noiseless, from the figure, then what we can see, this IN0 is dividing into the two parts. Okay, so one part is what, I naught by 2, and other part is also I naught by 2. So what I can see, so as it is seeing same impedances nearly of order of some small impedance, which I call, this is your IN naught by, both the transistors current are like this. Okay, so now I will see the individual voltage at output. Okay, so what will be the value of Vn1 out due to this I and I naught by n is coming from there. Okay, yeah, yeah. So how to analyze it? So yeah, this is the way. Now what I can see, we can calculate. Yeah, we can calculate a short circuit noise current, and this is directly coming. So this is nothing but a noise current which is coming at the output. Okay. So what I can see, this current, which is nothing but I n naught by 2, that I call I n naught by 2 is coming down. Also from this side, I naught n by 2 is coming down. Okay. So what this current is generating as a voltage at output, you can see directly. If I can say this is a short circuit current is coming from top side. Okay. Yeah. So if this is the short circuit current, better to write this as a V out one. I can represent it like this is my, that I call ICN one. I can write it in terms of short circuit current also. I can write this output voltage also. Okay, ISCN two at the output. So both the way we can write what is exactly the same current. So what voltage it is generating actually. Okay, so we have to see this thing. Yeah. So what is N naught by 2? Okay, yes. So this the noise current generated, yeah, noise current generated at first output is written as what? It is noise current times R naught 1, which is the output 1. Yeah? So what is the noise current at the output 2, and which is also minus IN naught by 2 R naught 2. Okay, so R naught 2 is nothing but looking in impedance at the output. Okay, here both the outputs. So what we can see, the one thing that I want to make point here is both these output noise voltage are correlated, because so this thing I should show here. So these are these two voltages independently. Now I'll relate and we'll calculate differential voltage. Okay, so there is one thing, when there is a common noise source and its noise is split into two halves, then what we can see, the point that I want to make here, this Vn1 out and Vn2 out are correlated because same noise source same noise source is responsible for generating both the voltages. Okay, yeah. So same noise current is responsible for both the voltages. So what is this? In1 out is minus in0 by 2 r out 1, en2 out minus in2 by 2 r out 2. Okay, so one thing, when two noise sources, so what is the differential noise? So now differential noise, or I should say exact the noise at the output is what? In general, what we do, Vn1 minus Vn2, sorry, I should write out as well. Okay, so this is the general expression, but it is a random quantity. So how we write this thing? We write like, we cannot directly minus it. What we will do, Vn1 square plus, let I should avoid this out as of now, or I should write out, otherwise you will be confused. Okay, so it is a minus 2 Vn1 out Vn2 out. So if they are uncorrelated, let's say if they are uncorrelated, then I will say this term is 0. But they are correlated, so this term is also coming into the picture. So what I can directly say, this is nothing but Vn1 square out plus Vn2 out square minus 2Vn1 out Vn2 out. So this is the differential noise. Now let's put these values. So what is the differential noise? That I equals to V out noise square differential noise, because the noise output voltages are correlated due to this common source of noise generation. Yeah. So what is this? I would say that I naught square by 4 R naught 1 square plus I naught square by 4 R naught 1 or 2 or 1. Yeah, one thing that I should make here, because of symmetric structure, I naught 1 equal, sorry, R naught 1 equal to R naught 2. The output impedance looking at both the outputs individually. Okay, minus 2 I 0 by 2 R naught I n 0 by 2 R naught 1. Yeah. So what this is making? This is making nothing but generating a square term. So it is in 0 r square by 2 minus in square r naught 1 square by 2. So overall what we can see, the noise is 0. Okay, so this thing I have shown through the calculation, rather we directly can say, because the circuit is exactly symmetric and you have a common tail current source which is giving the equal current to both the outputs, so we have generation of the same voltage, the noise voltage at the output. So they are going to be cancelled because we are subtracting and they are correlated sources. Now let's come to the second circuit. Then we'll see there is an uncorrelation in both the tail current sources, and due to that, effectively we'll see the noise is not zero. So okay, now I should make this analysis for the second circuit. Okay, so what is the second circuit? Let I should avoid our circuit. So this is our second circuit, and here what we'll see, these noise sources are uncorrelated because they are two different noise sources. Okay, so this is let's say n bias, this is p bias, this is vdd, v naught 1, v naught 2. Okay, so again when we want to consider the noise of both the current sources individually, then what we can see the individual involvement of the noise. Okay, so I want to make this thing like this. In the noise analysis, again we will short the input, and also one thing that I will like to make here is I will split this into R. Now this R, so this is the one noise source, and who is the other? Okay, so I can split my 2R like this. Okay, so 2R can be split like this. Now we will see the noise contribution at both this output. Out one noise, this is I call out two noise. Okay, I'm not writing completely out, it is taking more space. So yeah, so what we'll see, and now we'll see one thing. This is your noise current source due to this tail current, which is I call in0, and as they are identical with the values, but I will consider them non-identical as of now. Okay, their values are identical, they are same, exactly they are a copy of each other, but I will say they are uncorrelated sources, uncorrelated noise sources. Okay, so whatever voltage they will generate here at the output is also uncorrelated. So output generated by two uncorrelated sources are also uncorrelated. Okay, so what the mean by this point? If I want to find that what is my the difference of both this output or differential noise, and what we'll see, v out 1 n square. Okay, that thing should come inside the root. That thing come inside the root. Okay, that thing should come inside this root because anyway, now it's fine. We want to square value now, because here I have written only this the average value difference, so it is under the root. Okay, so here we'll see. Okay, minus 2 v out, so this entire thing come under the root. Okay, when they are uncorrelated, this term is 0. So what I can see, this thing is nothing but equal to v naught 1 n square, mean square value individually. So it is a root of this. Okay. So yeah, now you'll see the calculation for both v out 1 and v out 2. Yeah. So now what is the half circuit? I'm just avoiding the above transistor, but you can consider also. I want to see the effect here. Let it is a v out 1 n. I want to see the effect. So this is my R and this is my current. I am avoiding the device. I'm just taking the noise. IN 0. Okay. This I'm taking. So what we can see, my this current source has two paths. Okay. Also for the same, for the second, let I call this also at a time. Okay. So this current source also, which is a noise current source. Okay. Now I am representing the same value, which is really I was a dash, but you can see it is same. So the value is same. They are not correlated. Value is same, but they are uncorrelated. Okay, because two different sources are generating the noise, then they are uncorrelated. Okay, this part I should clear here. Two independent independent noise sources generate uncorrelated uncorrelated noise voltages and currents. Okay, yeah. So now what I want to make the point here, actually we are seeing the two paths. This current can come from this way and from this way, or we can split into the two halves. Let's say it is offering this, there is also one transistor, so let's say this is the current source is R, so we can calculate here also. So we can calculate the looking up impedance from both this point. Okay, so if this looking up impedance is small, let's say, so what I can see, the maximum of the noise current of this particular coming from this transistor. Okay, what point I mean to say, if there are two resistors, let's say the looking up impedance for this entire structure is order of 1 upon gm. Okay, let it is the order of 1 upon gm1, and this side it is R. Okay, so what is this? This is my noise current. Okay, so it has two paths to come. It has two paths to come. One is this and one is this, and this is the very low impedance. If I say 1 upon gm1 is lesser than this R, then I can say my complete current is coming from this, and this approximation if I am considering, and you can exactly calculate what the looking up impedance value, and depending on the R, so this is R up, so I call R up dash, it is same, the circuits are symmetric, they are same. Okay, so I can say the entire current noise is coming from upside, or it can be divided. Okay, this current can also be divided like R by 1 upon gm1 plus R times in0 is this current. Okay, same the thing, the division can be applied here also. Okay, this side also division can be applied. So what is the point? Now this current, let I say I not 0, means I should say, what I should say, x, let's say. So this is the after division, this is the x, and after division, let here I say this is the y. So these are two currents actually which are generating here also. It is R by 1 upon gm2 plus R times in0 dash, where I can say in0 equal to in dash, because the transistors are same or equal size, and everything is same for both the tail current sources. So then I can consider this. So these voltages are these currents are generating the voltages, and these voltages are, you can say, are non-correlated. So what I mean to say, Vn out 1, okay, Vn out 1 minus Vn out 2 is equal to under root Vn out 1 square plus Vn out 2 square. Okay, okay, both are uncorrelated, and this thing you can write V out 1 is what? If I say this I not x is coming down, then it is R not 1, and what is this? This is average. Okay, this I not 2. Okay, here I will say I not x after division is equal to I not y. So what it may look like, then when we will subtract them, they will be nullify, but they will not. The addition is not direct. The addition is this way. Okay, so it is in x square r naught 1 square plus I naught y square r naught 1 square. I will consider r naught 1 equal to r naught 2, the looking up impedance of looking up impedances at output. Okay, yeah, so what you can see, so this is the non-zero value, it is not equal to 0. So the conclusion of the discussion is that the previous circuit has the zero effect of noise at the output, but in this circuit the effect is visible. So if we consider the two circuits depending on the different aspects, and what we'll see, this circuit is better when we perform. The gain by both are same. Okay, so the conclusion is that gain buys both are same. Swing buys second is better. Noise wise, first is better. Okay, so these are the three things that I started this question with, these three viewpoints in my mind. Okay, so finally we got the conclusion that which circuit is better and what is your requirement. Depending on the requirement we can use our the circuit. Okay, depending on our specs, on our specs requirement, we can opt for these two circuits. Okay, and there are many other limitations. When we go for better noise performance, then we can see, I'm not exactly saying that what is happening in the noise point of view. But yeah, when we consider the tail current source, the tail current noise, then the second circuit is contributing some noise to the output. Rather, the first circuit is not contributing. There are other components also, but more or like the circuits are same, identical. So whatever the contribution of this noise, and current above current source noise, they will be maybe affecting equally at the output. Once you see this noise contribution of register one. So for the home, what is the home exercise? What is your homework? Analyze noise contribution. Analyze noise contribution of other elements of the circuit. Exactly, I cannot say which one is better, but depending on the tail current source, I can say first circuit is better in terms of noise performance, because the tail current source, noise of the tail current source for the first circuit is not contributing to the noise. Okay, so you can check exactly what the noise comes and what the input referred noise, then you can see it. Okay, so I think this is enough discussion for this noise performance analysis. And any other thing which remained, you can message me, and wherever if I missed something, you can tell in the comments, and you can personally send me your a message on Telegram. So you can personally tell me on Telegram. You can tell me on LinkedIn. You can also uh, put the comment in YouTube also. Okay. So these are three ways where you can connect. And if someone of you have my number, then you can also send me on WhatsApp. Okay. So I think this is enough discussion for these two circuits, noise performance analysis. Later, we will see the other CTQ problem. So this is enough for this video. Thank you.